People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
When you need mealtime inspiration, it's worth shopping Kroger, where you'll find over 30,000 mouth-watering choices that excite your inner foodie. And no matter what tasty choice you make, you'll enjoy our everyday low prices, plus extra ways to save, like digital coupons worth over $600 each week. You can also save up to $1 off per gallon at the pump with fuel points. More savings and more inspiring flavors make shopping Kroger worth it every time. Kroger, fresh for everyone. Fuel restrictions apply.
Every math problem, no matter how basic, has more than one solution. This is perhaps no surprise. You may have watched someone solve a math problem in a different way than you would have. You might have been taught different ways to solve a math problem, perhaps even in the same course. It's easy to intuit that this might be the case. The idea of technological progress, after all, depends on the ability to do the same task in different ways. There are even idioms, such as "there's more than one way to shear a sheep," that reveal a deep intuition that the property of being able to arrive at a solution to a problem in different ways is a universal feature of problems in general. Mathematicians often consider different solutions to the same problem, because different things can be revealed by each approach to the same problem. This ranges from simple arithmetic problems like addition and multiplication to complex proofs. So what are some examples of different ways to solve the same problem? What types of things do we learn by redoing problems in new ways? And what are some problems that have multiple famous solutions? All of this and more on this episode of Breaking Math. Episode 81. Correct. Now try again. I'm Sophia, and you're listening to Breaking Math. With me, I have on the hosts of Nerd Forensics, Millie Oriana,
Howdy doody.
and the co-host Jacob Urban.
Hello.
Today we're going to talk about different ways to solve the same problem. As always, we'll kind of start, what experience do you have with this kind of thing?
I mean, I remember having to do it in like classroom math problems and stuff like that. But a really great example, we actually did a whole episode about in Nerd Forensics about a video game called Hitman. And that's a great example of something that has multiple solutions of the same problem. Because essentially you're supposed to like neutralize somebody, and you can make it look like a gas explosion. You can push them down something. You can, make them get electrocuted. You can also just go in there and just shoot at everything.
Yeah, exactly. And that happens with a lot of open world video games. A lot of video games where there's a lot of interacting components that interact in their own individual ways, which is a lot like mathematics. Variables. You can't add x to y and get a new variable z unless you're defining z to be x and y, right? X plus y is not x times y. You know what I mean?
Yeah.
There are certain rules to math too, and so it makes sense that like I said in the intro, there's all these different expressions, many ways to skin a cat, Jacob, you're a woodworker. Can you talk about two different ways to solve a problem in woodworking?
Yeah. So the first thing that comes to mind is, the classic making a box, which you go with a classic box joint to secure your two sides together, or you could do dovetail joints to put them together. It's just however you want to do it, how you feel is going to look the best.
And can you use more than one tool, different tool to make a dovetail joint?
You can. There are a couple ways to do it. Within woodworking, a lot of tools are very specialized to do a certain task. But, you could, for like the dovetail in particular, doing like a sideways dovetail joint, because a traditional dovetail just looks like that. It looks like a dove's tail, and you use the wide end to secure the two pieces together.
Yeah.
But if you're doing it sideways, so instead of having it joining at 180 degrees, you now have it joining at 90 degrees. So that joining board has to be cut at a very specific angle because of the way the dovetail is shaped to secure it.
And I was just going to bring up, that's how you can tell a professional from an amateur. I'm an amateur woodworker who's done some woodwork in the past. Jacob is a pro because he didn't even suggest a butt joint. It never even crossed his mind. And I was thinking the whole time, well, you could just also do a plain Jane butt joint.
But see, as we can say, not only could the box be done with all these different types of joints, all different types of joints can be done with,
different tools.
Different tools. They could be done, like you said, for different parts of the box. And like Millie was saying, she has less experience with woodworking than you, but but because you all know all these, I'm sure you agree that if you taught a class in woodworking where you just taught somebody to make like 1,000 different types of boxes, you could get something pretty far, right?
Oh, yeah. Because here's the thing, I've made up my own joints, too, that don't, I've just been playing with wood and figured out how to link things together, and it was just weird joints that I've made.
Oh, yeah, and it's all geometry.
Essentially, yes.
And, Millie, the system that you're talking about is a lot of cause and effect, right? Mm-hmm. Which is an axiomatic system, really close to one, which we'll discuss it near the end of this episode. Yeah. Are we ready to begin?
Yes.
All right, so let's say that I asked you to multiply a number by 5, right? And you would and you want to do it like you do it in school. How would you go about that? I have some paper right here. All right, so I've written down a problem for you, Jacob. What is it?
371 times 5.
All right, so if you did it like you did in school, how much you go about it?
How I would go about it?
Or like if you did it like you learned in school.
Yeah. Okay. Well,
so you're multiplying the 1 by the 5, and you've written the 5 beneath it. You're multiplying 5 by 7, and you've written the 5 down there, and I'm guessing you're carrying the 3?
Yes. So I'm trying to figure out what is 5 times 7, and that's
35, yeah.
So that is 350 since it's 70. So that would be 355, and then that is 1,500. So you get 1,855. That's how I would do it.
Yeah, and that's a method that you've seen before, right, Millie?
Yes.
And yeah, you basically multiplied each component one by one.
Yeah, it just works easier for me to break it down and then add it together.
No, what's cool is that we're in a base 10 system, so there's actually a trick for dividing by 5.
Yes.
I mean, multiplying by 5, and that's dividing by 2 and multiplying by 10. And the way that you do that is this. All right, so 371 times 5. So one way that you do this is that you kind of divide by 2 and multiply and kind of shift over the decimal. So the way that we do this is, what is 3 divided by 2?
1.5.
1.5. So you write down a 1 beneath the 3, and then we just keep 5 in our heads, okay?
All right.
Now it's 7 divided by 2.
7 divided by 2 is 3.5.
3.5. So there's going to be another 5 that we're going to carry. So with the old 5 that we're carrying, we add that to the 3, because 7 divided by 2 is 3 and change. And we just write 8.
8. All right.
And it makes sense, right? Because we just carry the 5.
Because 5, yeah, 5 plus 3, 8.
Oh, yeah, exactly. And then 1 divided by 2 is...
1 divided by 2 is 0.5.
0.5, right? And we're carrying a 5 already?
Yes.
And then we take the 5 that we're already carrying, and we just pop it at the end.
All right.
So, yeah, I mean, you can see the advantages to this with larger numbers, right?
Yes.
Yeah.
I absolutely can.
And you could do the same thing with dividing by 5. All you got to do is multiply by 2 and divide by 10. So 371 divided by 5. What's 371 times 2?
371 times 2 is 742.
742, and then we just move the decimal place over. 74.2.
Interesting.
Yeah.
Yeah, and that's also the thing. If we want to multiply by 10, all we got to do is move the decimal point to the right, and then we want to divide it by 10, move it to the left.
Yeah.
All right, so do either you know 25 by 25 off the top of your head?
25 times 25? Mm-hmm.
If you don't know it off the top of your head, let's pause on that.
Yeah, I don't know it off the top of my head.
That's 150. No.
Well,
I did
way higher
something
than that.
weird. I did 5 times 25.
Well, actually, you know, that's the thing.
That's
is that
halfway there.
if 20, we use the property that 25 is 5 times 5, right?
Yes.
So we could actually multiply it by 5 4 times. We could start with 5 and multiply it by 5 3 times, right?
Yes.
And just for kicks, do y'all want to do that with the halving system they showed?
I can try. Okay, so what we're going to do is I'm going to divide it by 5 first, right?
Well, not divide it by 5, multiply it by 5.
Multiply it by 5.
And the do that so we start with the 5, right? Mm-hmm. And what's half of 5?
2.5.
2.5. So we just write 25, right? Because we carried the 5 at the end.
Yeah.
I mean, we don't put the decimal there.
Yeah.
All right. So now what's half of 25?
Half of 25 is going to be
12.5.
12.5, yes.
So 125. And what's half of 125?
Half of 125 is going to be 62.5.
62.5. There we go. 625 is 25 times 25.
Ah.
I mean, do you want to give it a just for kicks? Do you want to do 125 times 125? All you have to do is multiply by 5 2 more times.
Yeah, sure.
You do the next 2 lines.
Okay.
So we're at 625.
And 125 times 125 is what we're going for now.
Yeah. So all we
So-
need to do is since this
Multiply
is already
it by 5 2 more times.
yeah, because 25 times 25 is 125 times 125 divided by 5 twice, right?
Yeah.
So multiply it backward. Yeah.
So half of 625 is going to be 312.5. Half of 300 or 3125 is going to be 1,563.
Let's see. Well, we're carrying a 5, and 2 divided by 2 is 1. So yeah, 60.
62.5.
Yeah, 15,625.
Yeah. So 15,625 is what we're at. So that's it.
Yeah, and you see how easy that was?
Yeah.
Yeah, and you get an intuition for how to kind of do this stuff. And these are, I mean, this is a really nice example. I mean, I don't want to go too far into this type of math because we have a lot of stuff to cover on this episode. But if we're interested, we mentioned on the show before, Trachtenberg speed math is what this is related to. It's a system that created by a concentration camp victim who developed it to keep sane in the camps.
Oh, wow. That's fascinating.
Yeah, right. Now, Jacob, in your day job, you work with money, right?
Yes.
So what I'm going to say is American money, that just for people who don't quite know, we have a 25-cent piece, a 10-cent piece, a 5-cent piece, and a rarely used 50-cent piece, and an even more rarely used dollar piece. But Jacob, given the property that 25 cents is equal to a quarter, what is 31 times 25? How much would 31 quarters be worth?
Yes. 775.
Yep. So yeah, I mean, it's $7.75, right?
Yes.
And I feel like it's sometimes useful to use that because our minds are it's easier to think sometimes in terms of money, you know, because our brains just work with it every day.
Yes. Here's the thing, though. If somebody gives me 31 quarters, I'm usually very upset at them.
Oh yeah, definitely. All right, and finally, we're gonna do 25 times 25 again. We're gonna use this property. A plus b squared is equal to a squared plus 2 times a times b plus b squared. Right? So
Yeah.
25, if we do that as 20 plus 5, what's 20 squared?
20 squared is...
It's just 2 squared times 10 squared, right?
Yeah, 2 squared times 10 squared, yeah.
Yeah, it was 2 squared,
4.
10 squared.
10
100.
squared, 100.
Yeah, so it's 400.
400.
And how about 20 times 5?
20 times 5 is 100.
Times 2.
200.
And then finally 5 times 5.
5 times 5 is 25.
So you add the 400 to the 200, you get 600 to the 25, and you get 625.
Huh.
All right, so now we're going to do another problem. We're going to do a multiplication of a 3-digit number by a 2-digit number, right?
Yes.
So we're going to do 527 times 39. You know, we've done the write it out method, right? How would you do that? You just do row by row, do digit at a time, right?
Yes.
Yes.
Well, what I'm going to teach y'all how to do today is the old French way that were used by French peasants. All right, and this is how it's done. So what you do is you write 527 and you write a 1 next to it. What's 2 times 527?
1055. No, 1054.
I'm going to write a 2 there. And then double that, so you get 2108, and that's and you double that too. And then 4216, you write an 8. Let's see, what's the next one? 8432, 16, and then 16,864. Is that right?
Yes.
All right, yeah, 16,864 next to 32. All right, and now we stop because if we double 32,
You'll go way over.
we'll go way over 39, right? So here's the thing: we start with 39, and the first number that is bigger than that is smaller than 39 is 32, right? The
Yes.
biggest number, that is. So Jacob, write down 16,864, and then we put an X next to that. And then, and then what we do is that we subtract 32 from 39, and we get 7. Now, what's the biggest number smaller than 7 there?
4.
Yep. And so now write down 2,108 underneath that number you just wrote, Jacob. So yeah, did you write 2,108 underneath 16,864, Jacob?
Yes.
All right, so 7 minus 4 is...
3.
Smallest number, and okay, Millie's biggest number there's on the right-hand column, smaller than 3.
On the right-hand column, smaller than 3 is 2.
Yep, so write down 1,054 beneath that, Jacob.
Yep.
And then finally, 3 minus 2 is...
1.
And so finally, we just write down the last one, too, which is 527.
Yes, yes.
All right, and let's see, do you want to add that all up?
So I got 20,553.
Yep, that's the right answer.
Okay.
Now, Millie, did you notice anything peculiar about this method? Something perhaps modern about it, even though it dates back to the Middle Ages?
The fact that it's algebra, right?
It's not even algebra. It's a type. It's a type of arithmetic. But if you notice the list of numbers on the side, 1, 2, 4, 8, 16.
Mm-hmm.
It's a method of binary multiplication.
Yeah.
Discovered by French peasants.
Fascinating.
Oh yeah.
That's really fascinating.
Well,
I mean, I guess when you have nothing else to do all day but toil.
well,
I mean, you need to toil and calculate how much you owe your lower. No, obviously.
well, yeah. Well, also, the aristocracy is not letting you learn real math, so you have to come up with something to make sure you're not getting screwed on your grape harvest.
Honestly,
or whatever.
this is about as good as the real math of the day.
Well, yeah, but they're not allowing the peasants to go to their colleges and stuff.
Oh,
If
yeah.
you're a farmer, you need to know you're getting paid appropriately.
Oh yeah, and there's so many reasons
And
why
you need to know if you're paying the right amount in taxes.
Yeah, French is actually interesting. Just side note about French is that they count in a sort of base 10 and 20 at the same time. Like the 60 is 3 20s, for example. 70 is 3 20s and a 10.
Interesting.
There's a hospital that has a really old-fashioned name called 1520s. I don't know if it's still open, but it had 300 beds. That's why it's called 1520s.
Interesting. That's a very interesting system.
All right, so now we're going to do the square root of something, and we're going to assume that we have a calculator, but the calculator can't do square root, right?
Yes.
So let's do the square root of 3 by trial and error, okay?
Okay.
Ready, Millie?
All right.
You take the first guess for the square root of 3.
Square root of 3 is going to be, isn't it 1?
Well, 1 times 1 is 1.
Yeah, so it's
What times what is 3?
1.5.
So let's just say 1.5 was the first guess, right?
Yeah, that's hard.
So yeah, it's 2.25. So the square root is going to be what, higher or lower than 1.5?
Higher.
So Jacob, give me another guess.
1.75.
All right, 3.0625. So
Well, up.
we're over by a teeny bit. Millie, give me the next guess.
1.67.
2.78.
1.73. Okay, so it's gonna be about that with some extra hanging off the edge.
Yeah, let's see if we go for another digit. Millie?
All right.
Look, we're at 2.9929.
All right, so 1.734. 732. 733.
So it's obviously between 2 and 3, right?
Yes.
So-
So 2, 1. Still not right.
So it has to. Yeah, the next digit has to be 0, right?
Yes.
0 what?
0.01.
0, 1 maybe.
And so on, right? And
Yeah, you just keep going until you
Yeah,
get
until you get to
closer.
Yeah, and that's one way you could do it. And what's interesting is we'll get the amount of digits per guess is constant the further we go down, right?
Yeah.
But now we're actually going to. This is the way that the calculators and actually the ancient Babylonians did it. So what you start off is your guess, right? 1.5, right? Millie?
Mm-hmm.
So what you do is you take the average of 1.5 and 3, which is a number we're trying to take the square root of, divided by 1.5.
Mm-hmm.
The next guess is, what does that say?
1.75.
1.75, 1.73214, and see, and we're 73205, and see, it got the digits way quicker.
Yeah.
But yeah, that's because it's obviously an algorithmic way of doing that. But yeah, that's the way that calculators do it.
Interesting. I don't think I could do that in my head, or even with my hands and a tablet.
Well, yeah, I mean, the key is just you have to take the average of the number, the average of your guess, and the number you're trying to take the square root of divided by your guess to get the next guess.
Did you say it was Babylonians or Byzant? Okay. Yeah, no, because I'm just imagining some poor Babylonian dude pressing his little stick into a clay tablet trying to figure out math problems.
I mean, if you've seen a modern reconstructive archaeologist, though, yeah, it's a very quick way of writing too. It's just it's just as quick as ours, actually.
Yeah,
actually,
yeah.
pretty much any way of writing is about as. Okay, that's not true. They're not all about as quick, but they're within a few magnitudes of one another because there's shorthand and things like that.
The problem is that, he has to go through this by hand, the 1.732142857 plus.
Well, here's a cool thing though. In ancient Babylonian math, this many digits of you don't need as many digits of accuracy because you use base 60 digits.
Yeah.
So that's the thing about the Babylonians is they had a lot of tables they looked up. So there's this tablet. Hold on, let me look it up.
Yeah, somebody figured it out before them, and they would use it as a reference guide.
Yeah. So for example, Plimpton 322 was thought to be an accounting record for a long time. It's this document right here.
Yeah.
Millie?
Mm-hmm.
That's Plimpton 322.
Yeah.
And it turns out that's actually a set of Pythagorean triangles.
Really?
Yeah, and the dimensions to them and a general formula for calculating them.
Yeah. It's fascinating.
All right, so now we're going to do volume of a pyramid. All right, so this is Euclid's proof of the volume of a pyramid. In earlier parts of Euclid's Elements, it's Euclid Book 12, talks about how pyramids of equal bases have equal volume and things like that. But this is the proof that shows the actual ratio of the volume of a pyramid to you'll see here. So as you can see, it's a triangle that's been extruded. And the way that Euclid's done here is he's cut it into 3 exactly equal pieces. And can you see why they're equal?
Yes.
they take up the same amount of space.
Yeah, exactly. And if you look at these, because if you look at the distances that they all cover, they all have the same like like there's one going across the diagonal here, and here and here. You know what I mean?
Yeah. So they're all it's just 3 shapes of the exact same dimension put together.
So right there, you could 12 book 8. You could book 12 part 8. Is that similar pyramids at which triangular bases are in the triplicate ratio of their corresponding sides. So that's a ancient Greek-y way to say 1/3 of base area times height.
Interesting.
Another way that we could do this is with calculus, which was developed much later. So if something is if a square is half as big in every dimension, it's going to be what times the area of the original square?
2?
Well, a quarter, right?
Yeah, quarter. Yeah.
Yeah, because 4 of them will fit into the original area.
Yeah.
So that is to say we squared the area as we go down. So if we do the integral from x equals 0 to, let's see, to h of area times h divided by x squared. Let's see if that works. Yeah, see right there, area times height over 3. You get the same exact formula of 2 different methods.
Interesting. Yeah. That's really cool.
Yeah, and that was for everyone who couldn't understand my mumbling. The integral from x equals 0 to h of a times x divided by h squared dx. And the reason why is, like we said, the ratio squared of the individual length components is the ratio of the area components. And using there's actually a similar thing that we could do for the volume of a sphere. So actually let's talk about Archimedes' calculation. What this is right here is a sphere, right? Mm-hmm. It has a cone going halfway through it, so that the cone intersects the sphere halfway through.
Yeah.
The tip of the cone is at the top of the sphere, so the cone penetrates the sphere. And then around that, you have actually a cylinder. And what you do is that you show that the volume of the sphere is equal to the cone. Is equal to the cylinder minus the cone. And the way that you do that is by. All right. So yeah. So the way that you do it is that if we have gone, let's say like x down here, right, and has radius r. Mm-hmm. The amount that it goes out here is just x. So the area of the cut of the cone in that case is just x squared. The sphere, however, you can use a property that the distance from here to here is a radius, and so that means that radius is a square root of radius squared minus x squared, so just radius squared minus x squared, and that's how far that goes out. And the very last is this outward piece, which is just radius squared. And radius squared indeed is radius squared minus x squared, right? I mean, radius squared minus x squared is radius squared minus x squared, right?
Yeah.
It's almost tautological.
Yeah.
And that's how you calculate the volume of a sphere.
Interesting.
And just to prove that we could do it another way, we can also do it this way. We take here the integral from theta equals 0 to 2 pi. And we're not going to do the full calculus problem, but basically you can set it up in either the spherical coordinate system or the cylindrical coordinate system or the Cartesian coordinate system. And you take basically a triple integral, and you arrive at the same volume of the sphere, which in each case is 4/3 pi r cubed. All right, so now we're going to do 2 plus 2. How do we do 2 plus 2?
You can just add them together.
You can get 4, right?
Mm-hmm.
Yeah.
Or you can multiply 2 by 2.
Well, that's a different problem, right?
Technically.
Yeah, I mean, I guess you could factor it out like 2 times 1 plus 1 equals 2 times 2. Yeah, I guess you could change it to that. But what you could also do is you can use piano arithmetic. So piano arithmetic is, we talked about it, I think, on a few previous episodes. But it has a few rules. Is that there's a thing called a natural number. The thing after a natural number, the successor is what it's called, is also a natural number. The sum of 2 natural numbers is equal to the sum of some number n plus the successor of m is equal to the successor of n plus m. And those are the only rules you need to know. Oh, and we also need to define that the successor of 1 is 2, the successor of 2 is 3, successor of 3 is 4. And I know we've done this on another episode, but it's one of my favorite examples of a problem made unnecessarily complicated. So we start with 2 plus 2, right?
Mm-hmm. Yes.
So 2 plus 2 is the successor of 1 plus the successor of 1, which is the successor of the successor of 0 plus the successor of the successor of 0. So now we got the problem down to its base form. Now n plus the successor of m, so we call this m in this case, right?
Yes.
Is the successor of n plus m. So we copy n, and then we copy m. And now we just need to figure out what this number is. So subproblem. So we just use the same property as before. And then we end up with the successor of the successor of the successor of 0 plus 0. And one more fact we need to know is that anything plus 0 is just that number that you started with. So that would you end up with the successor of the successor of the successor of 0, right?
Yes.
Yeah.
And the successor of that is you just add another successor, right?
Yeah. Yeah.
Does this just keep going?
Nope, we're almost done.
Okay, I was almost afraid it just kept going infinitely for a minute there.
No, the successor of 0 is 1, right? So we can replace that with 1.
Yeah.
So we defined that earlier. We've also defined the successor of 1 as 2. We defined the successor of 3. Successor of 2 as,
3.
Spoiler alert, 3. And the successor of 3 is
4.
2 plus 2 is 4.
Yeah.
That is horrifying.
Is this why you make things so complicated sometimes? And I'm like, we could just buy a thing for this.
It is sometimes programmer syndrome to do that. Yeah.
Yeah, because like that was crazy.
Oh, I know. Oh, yeah. Like, you could ask anybody who knows me. You know this. I'm telling the audience this. But like, after I've been doing math problems for a while, sometimes I'll talk like I'm still doing math problems. You could both attest to this.
Yes.
Yes.
Now we're going to mention another problem that has a few famous solutions. We're not going to go through the solutions, but we're going to mention it because it's an example of a problem that was very fruitful in different ways to solve it, and that's the brachistochrone curve, or the shortest. So if you rolled something down a path, right, like a straight path,
Yeah.
turns out that that's not the quickest way to go from this point to this point.
Yeah.
It actually is a curved path called the brachistochrone curve.
Interesting.
And it's a type of curve called a cycloid. And a cycloid curve is if you put like a light on your tire and you drive down the road, that it traces out a cycloid. A cycloid is just like something traced out by a moving, spinning circle.
Interesting.
And the brachistochrone curve turns out to be this. And one of the early solutions showed it was just a geometric in nature, and showed that it had to be this kind of curve because of the type of curvature that it used. It was a very classic geometry type solution. Newton invented actually calculus of variations, which is the idea of basically treating an entire function as a zero. So treating, basically it's a way of finding minimal functions, not just minimal values of things. And that was developed because he got the problem posed to him of the brachistochrone problem. Another solution that was really famous is of an imaginary substance that was like made out of glass, where the refraction, the index of refraction, which how much it bends light, increases as in proportion to gravity, and the path that a beam would trace out is actually a brachistochrone curve that you need.
Oh.
So yeah, that's just a famous problem like that.
Okay, interesting.
And then finally, we're going to talk about the Gödel incompleteness theorem. So you might think, there's so many ways to solve a problem. You might think that if it's two different problem-solving systems, you could solve any problem any number of ways in both those systems, right?
Yeah.
Well, it turns out that some problems are not solvable in some systems at all. So, like, for example, there's a problem that was demonstrated in the 1970s I can't remember exactly what it was, but it was a demonstration that piano arithmetic, which is the kind of arithmetic we were talking about earlier.
Yeah.
And even the more analytical version of that, which was fleshed out by people like Cauchy in the 1800s, was not able to. I mean, I guess you don't need the Cauchy stuff because it was just talking about the integers. But yeah, the piano arithmetic was incomplete for a problem that could be solved in a completely different system. However, in that other system, because there's one way to solve it, you can if you can modify any one good step into two different steps, you've now created a different way of solving it, right?
Yes.
So no matter what, if you have a way of solving it, you can make definitely an argument that there's an infinite amount of solutions in that system. But there are some systems that, even though they describe the same type of problems, have no solutions to the same problem.
Interesting. Yeah, and it makes sense. I mean, it's kind of like approaching any problem. There's the right tools for it, and there's the wrong tools for it, and sometimes you can change them out.
Oh yeah, for example, with set theory, a naive set theory leads to some problems. So set theory is being built in the 1800s, and people are making all sorts of strides. Okay, so Russell's paradox was come up with in the idea to a universal set. So the idea of a universal set is like a set that satisfies certain properties, right?
Yeah.
But so Russell asked, does a set of all sets that doesn't contain itself, the set of all sets that don't contain themselves, does that set contain itself?
No.
If
Maybe.
If it doesn't contain itself, then it must contain itself because it doesn't contain itself.
Ah.
But if it does contain itself, then it can't.
Makes
So it
sense.
shows that just going like a naive approach, you run into paradoxes. You also run into like situations like, and it turns out that you have to like choose which axioms you use. Like it turns out that using the axiom of choice, for instance, means that if you take a sphere and you cut it up into an infinite amount of different slices that are each these like kind of infinitesimal points, rearrange them and then put them back together, you can get two spheres out of it.
Huh. Interesting.
That's a Banach-Tarski paradox. But if you don't take the axiom of choice, you can't do that. And if you can't infinitesimally divide things, then you can't do that. So you can't do that in a material universe. With set theory, you have ZFC set theory. You have other formulations of set theory. But yeah, so that is to say, yeah, they're basically the right tools for the right set. And you can always improve on your tools. That's the thing. But as Gödel has shown like conclusively, there's no way of making a perfect set of tools at all.
Oh, yeah.
There are so many problems and more ways to solve them, and perhaps even more revelations from the ways in which they can be solved. We've walked through a few problems and shown you how easily you can gain a new perspective by changing your approach, and why you can almost always see new things from each perspective. I'm Sophia, and this has been Breaking Math. Y'all want to plug your podcast?
Yeah, it's Nerd Forensics. It's also part of Santa Fe Trail Media.
It is.
It is amazing. It's a little bit more of a rest for your brain, in the sense that you don't have to do math, but it is kind of we do tell a story, and you got to memorize like some events and stuff sometimes. But
Oh yeah, and I mean it's also a little bit more adult oriented.
yeah, we definitely get a little blue. But we also just talk about insane things. Like we have an episode that'll be coming out really soon about crazy sports stories. And Sophia actually gets to tell a sports story in that that has to do with mathematics.
Oh yeah. So if you want to check that out, check that out.
Yeah, and that'll be our next episode coming up. And that should be out by the time this episode's out.
So any final thoughts about all this craziness about multiple problem solving methods and stuff?
It makes perfect sense to me because there always should be multiple solutions to every problem.
Oh yeah, it makes sense.
Yeah, and I mean, just the differences between people in general, I feel like everybody's going to look at things differently, therefore they'll have a different solution to a problem.
Oh yeah, absolutely. And I mean, that's also why it's good to have different perspectives, like, from different cultures and stuff like that, because different cultural perspective can change the way that we approach something that seems even as rigid as mathematics. Like, there's so many examples that, I mean, that could honestly be a whole other podcast, and probably should be another whole other podcast.
Yeah.
Final thoughts, Millie? No, I already asked you.
Yeah.
I'm all getting tired. This was a big episode. Good night, everybody.
Good night, everybody.
Good night.